Hello everyone, a very good morning. Today we are going to discuss about Eagleeye. It is not only about how to build an efficient data pipeline for anomaly detection, but also to enable every one of you to go back to your homes and build such a framework for yourself. If I have to talk about myself a bit, my name is Tuhin Sharma. I work as a senior principal data scientist at Red Hat. I started my career at IBM Watson in data science. I ran my own startup and I worked at multiple companies before joining Red Hat. So I'm very excited for this talk and interacting with you. And the whole idea is to learn together and grow. So let's dive into it. The outline that I decided would be really great to have is this to start with. First, we're going to talk about what is the problem we are going to solve, the architecture that we chose to solve the problem. We're going to talk a lot about real-time processing. The age of big data is kind of mature a lot, and now is the age of fast data and high velocity data. So we'll see how we are going to tackle that scenario in the architecture. Then we're going to talk a bit about anomaly detection, and eventually we'll actually go through different visualization techniques. In the end, I will show you a quick demo. The code is open source, so I have included the link to the GitHub repository in the reference section of this slide. The internet is exploding day by day. If we look at 2019, there is an estimated 4.1 billion people out there who are using internet. And there's a 5.3% year over year growth that we have seen. And that was just before the COVID broke out. We can all imagine, as we are all confined in our houses, what could have been the internet usage over the past 2 years. If we look at global penetration rate, it has increased from nearly 17% in 2005 to over 53% in 2019. So that's a massive, massive growth. Due to the use of so many VMs, containers, different cloud providers like AWS, GCP, IBM Cloud, Azure, and of course, hybrid cloud, that is a combination of on-prem and the public cloud itself, the threat surface is actually increasing exponentially day by day. Now, the people who are responsible for actually monitoring this and take preventive measure is called Security Operations Control Analyst. So if we look at a big telecom company, they always have SOC analysts who monitor the interactive events that is happening over the network, and they try to identify threats before they go out of control. But the job is becoming very complex and difficult because of multiple network policies, millions and billions of network requests that is happening every second, and the exponential growth rate of network connections. These are the challenges an SOC analyst faces on a daily basis. The denial of service when a part of the network stops working because of the bombarding of the request that it receives. The second challenge is data loss, that is permanent or temporary loss of data from the network. And finally, the data corruption, when a malicious agent come and live on the network and they corrupt the data. The problem is not new, and there are existing malware-based solutions. So all these anti-malware companies have a big ledger of all the popular malwares. The malware could be a virus, a worm, a tool, a rootkit, spyware, a ransomware, etc. When an agent or malicious user or IP address or somebody who is behaving irrationally in the network, uh, its signature is actually matched against this directory of the malwares. And if there's a match, then that particular entity is quarantined. Otherwise, the particular entity is just free to roam in the network. But the shortcoming of this solution is the evolving nature of the agents. So every day, millions of new malwares are created and injected in the network. And there are malwares which are self-programmed to evolve themselves over time. So once new spyware or malware actually comes into the network, or they evolve into something new, it is really impossible to identify them from a lookup directory or database of malwares. So we cannot actually detect them and they just do what they're supposed to do and things go south. That is why machine learning is gaining a lot of popularity in detecting this sort of threats. The reason is machine learning is not entirely a rule-based thing. It is not only a signature matching process, rather it is a behavioral thing. So once the model, that is the AI engine, knows about certain known malwares and their behaviors, it can correlate with unknown entity's behavior and figure out what is the probability or the propensity of that particular entity being a threat. If we look at the network events, it is nothing but a time series of data. Data could be a file or byte information or location information. So if we can analyze these network events and we can find anomalies in them, we'll be able to identify potential threats as well. So we can pinpoint that this particular IP address for the past 2 hours is behaving irrationally compared to other IP addresses in that time frame. So probably something is wrong with that, or there's a need of quarantining that particular IP address. Over the coming slides, we shall discuss how exactly we can design such system and how exactly we can alleviate such problems before they actually affect us at mass scale. We're going to discuss about the architecture, and then we are going to talk about the components in that architecture and how we came to choosing different tools for each of those components. So we are going to follow a top-down rather than a bottom-up approach. This is the data flow architecture. Data sources are actually scattered. So if we talk about a telecom operator, the data could be present in multiple private data centers or public cloud as well. Data could be user info, that is the username or email ID through which user interact over the network, or it could be the IP addresses. Then the data could be a network event stream, which is timestamped event. It may include byte information also, which is present in each of those requests in case some file is being sent. So anything related to the network which is being sent or interacted between two entities. The entities could be, of course, user or IP. So that's what we call as the source of data, and that is what we want to capture even to start this whole flow. So after we identify the data sources, the next step is to ingest that data. That is, we have to make that data platform ready so that we can actually fit it into various data pipelines that we already have in place. As I'm talking about real-time network events, those events need to be ingested in real time, because when we are detecting network threats, we really cannot wait for a day before saying that, hey, yesterday in the morning there was a malicious user or IP that I detected just now, but now it's too late because whatever that malicious activities that particular entity was supposed to do, it probably had done that already. That is the reason the real-time ingestion is really important, so that we detect any such threats as soon as possible before it goes out of control. Then there is batch ingestion. So there are certain data which is, let's say, the ISP data or something like that, which does not change drastically over time. And it is not very time sensitive as compared to the network event stream. So those data can be ingested in batch. After that, the data from the various sources will have their own format. So there's a need to normalize the data so that the platform understands the schema and then it is platform ready. So once the data is platform ready, the next step is data processing. So we have to do data enrichment by including data from various external data sources. To do the data context generation, we need to extract or add different features. The data becomes now AI ready, and we can train different AI models on top of that. So data ingestion is to make data platform ready, while data processing is to make the data AI ready. That leads to the fourth step, which is AI engine. One component is the machine learning, where we learn about behavioral aspect of different entities from the events. Then we have incremental training. So let's say yesterday I actually processed 100 million records, and based on that I trained a model. Today I have got, let's say, 10 million additional records. So I should not retrain the model on the whole 10 million plus 100 million records. Rather, we can say that, hey, you're already trained on 100 million records, so I don't want to train you on those 100 million records again. Rather, I want to fine tune the model parameters based on the new incremental 10 million records that has come today. So that is the incremental training. And eventually the active learning, because the data that we are actually dealing with, the main challenge is they might not have a known fingerprinting. So we don't know the label beforehand, and that's why the need for active learning is there. So we are going to keep training the model and going to identify the threats. Definitely we are going to hit and miss some of the threats. If you are missing some and we identify that these are the threats we missed, then we label them and use that data to fine tune the model. Right? That's how we can actually actively learn from the data and improve the model. Eventually, the last step is analytics. We need to consume this information eventually in a human readable format, and that is why the visualization is really important. Now as we now look at the real-time aspect of it, we need to have a way to visualize data also in real time to gain actionable insight. So overall, this is the high level data flow architecture that we have. Now let's deep dive on the product architecture. So on the left hand side, if you see, there is the data sources where the data is coming from multiple VMs or containers or network traffic data itself. It is coming to the data engineering block. Inside data engineering, you will see data ingestion and data processing. So data ingestion is to make data platform ready. Data processing is to make the data AI model ready. So the tools that we are using for data engineering part in this case is Kafka and Flink. After the data ingestion and data processing is done, everything is constantly being synced to the data storage, which is Apache Pinot. It is a OLAP DB, and that is where the data is constantly getting synced. As soon as the data arrives in the Kafka topic, it gets into the Pinot. In Pinot, we have the raw events, so we have the ingested events, and we have the processed events, which can be used directly by the machine learning models. Then we have the AI engine. There are multiple techniques like isolation forest, 1 plus SVM, k-means, autoencoder by using tools like sklearn, pytorch, spark mllib, which actually takes the data from Pinot, trains the model, and the model is then stored in MLflow model storage, where we can do versioning of the model. We can compare the same model, train on different volume of data. We can move models from dev to stage to prod. So all this cool stuff we can do using MLflow, and that is why we have that as model storage. The scoring is also done on the profiles of these entities, and they are getting stored back to the PinotDB. Eventually, PinotDB is going to power the Superset real-time dashboard. So Superset is a tool that we are using for our real-time dashboard visualization. Now let's deep dive into individual components. The 3 components we shall discuss are Kafka, Flink, and Pinot. Apache Kafka is a distributed event streaming platform. Here we shall talk about the differences between queuing and streaming and the rationale behind choosing Kafka. Once it comes to queuing versus streaming, the fundamental difference between these two are the way they operate. The message queue is a producer-consumer model, so you can have one or more consumers and producers in a message queue. Multiple consumers actually start listening once the data arrives. The guarantee is that the message will be delivered only once. For streaming broker, it is a pub/sub model, where messages are organized in a long file frequently called as topics, and one or more consumers actually subscribe to the topic or the log file to listen on the data. So with the proper setup, same message can be actually delivered to all the subscribers without even doing any replication. So that is a fundamental difference. In the message queue, each message is delivered only once. So once it is consumed, the message is gone from the message queue. On the other hand, in the streaming broker, the message is available even after it is consumed. In a message queue, it may not be delivered in the same order, but in the streaming broker, it is always delivered in the same order given they're in the same partition. Now, in the context of anomaly detection pipeline, streaming broker is the right choice because we are going to do multiple things with the event data. We are going to create profiles around the IP addresses. We are going to create profiles around the user information. We're going to create profiles from a location perspective. So many IP addresses are coming from a particular location. How many requests are being generated by a single IP address? So all these things we are going to derive from the same set of events. So it will be much easier and convenient if we follow a pub/sub model where we have multiple consumers which will have their own profile aggregation logic inside them so that it can read the same stream of data, but do different things at the same time. This is a comparative analysis between Kafka and RabbitMQ. Message ordering is supported in Kafka, but not in RabbitMQ. In RabbitMQ, once message is consumed, it's gone forever, but in Kafka, it's always there. In Kafka, there is a retention period you can actually set, but you can always set it forever as well. For message delivery, Kafka guarantees atomicity, while RabbitMQ does not. Message priorities is not supported in Kafka, but RabbitMQ it is supported. If we look at the performance with limited resource, Kafka reaches a very high throughput, but for RabbitMQ it requires a lot more resources. That's why we choose Kafka for the first data engineering piece. Apache Flink is a distributed real-time processing engine where we are going to talk about fundamental difference between microbatch processing and stream processing. And eventually we shall talk about why Flink and why not Spark streaming. So in the microbatch processing, the system only checks periodically when the data is coming and when the next batch window occurs. And based on that, it actually processes for the whole window. But in case of stream processing, the system continuously monitors for new event in the system. And as soon as it comes, it just processes it. That's why in microbatch processing, there is always a delay And if you are creating a data pipeline where each of those components of the pipeline are working in a microbatch fashion, so that delay gets added and gets accumulated. But in case of stream processing, the processing is done as soon as possible, and that is the reason stream processing is gaining very much popularity when it comes to real-time processing. While having most up-to-date data is not important and the tolerance of slower response time is a bit higher, for example, offline analysis of historical data or identifying correlations or finding patterns in previous month's data, in those use cases, microbatch processing or the batch processing is in general works well. But for final cell transaction processing, where the impact or cost of being wrong is very high, for example, real-time fraud detection, the real-time pricing, in those cases, the stream processing has better application. So why Flink? Flink represents the real-time processing because it is the first true streaming framework with all the advanced features like event time processing, watermark, etc. Of course, there is Apache Stream. Spark streaming is not truly streaming, rather it actually slices the whole stream into multiple chunks and then processes them with batch parsing approach. So when it comes to data latency, Flink actually processes the data at row level or at record level, but in case of Spark streaming, it processes the data at an RDD level, which is the basic unit of data in Spark. When it comes to adjusting different parameters to make it work in data pipeline, it's mainly auto-adjusting for Flink. And not too many parameters you'll have to tune, but in Spark streaming, there's so many parameters to tune, and that's why it is very hard to get it right. So if you don't have an expert DevOps who understands Sparks really well, it is very difficult to get it working right. The community support for Flink is not as big as Spark, but it is growing at a rapid pace. But for Spark streaming, I mean for Spark community is a huge, and hardly there would be any data engineer who didn't work on Spark. So these are the differences between those two tools, and Flink is something that we use because we want to do it at a true real-time perspective. So we need to capture the data somewhere, and that's why there's a next component, which is Apache Pinot, which is the real-time distributed OLAP data store. So here we shall discuss about what's OLAP and why are we using Pinot. So OLAP tools enable users to analyze multi-dimensional data interactively from multiple perspectives. So it consists of three basic analytical operations. Rollup, it involves the aggregation of data that can be accumulated and computed in one or more dimensions. For example, all IP addresses are rolled up to a zip code level or geolocation level. Drill down is a technique that allows the users to navigate through the details. So for instance, a user can view the behavior of an IP address at an hourly level. Slicing dicing is a feature where users can take out a specific set of data and view the slices from different viewpoints. So these viewpoints are sometimes called as OLAP dimensions. So the example could be looking at the same network traffic data by IP address, by geo, by date, etc. So what is Pinot? Pinot is designed to answer OLAP queries with low latency on immutable data and mutable data with upsearch support. It supports pluggable indexing technologies like sorted index, bitmap index, inverted index, JSON index, etc. It supports near real-time ingestion with Apache Spark, Apache Pulsar. Kinesis supports JSON, Avro, Protobuf, Thrip formats. It is horizontally scalable and fault tolerant. Joins are currently not supported, but the problem can be overcome using Trino or TrustDB for querying. It has SQL-like language called PQL that supports selection, aggregation, filtering, all the popular operations of SQL. It consists of both offline and real-time table. So you can use a real-time table only to cover segments for which offline data may not be available yet. And it supports ML algorithms to detect anomalies on the data stored in Pinot. We can use a Thorai with Pinot for anomaly detection and root cause analysis, but in this talk we shall create our own anomaly detection model. So let's talk about the anomaly detection. We're going to talk about our journey and the tools that we use to build the AI engine as we saw in the architecture. Our journey has been like this. So we first started with very simple approach with simple rules. If we know in an hour a particular IP address is sending more than certain threshold of request or more than certain threshold of files, then just mark them as anomalies or irrational entities. Then we gradually move to G-score, where we capture various features like the number of files sent over time. Then we calculate the Z-score, and based on that, we actually score different entities. These were not a really good way of doing it, but that was a start. Then eventually moved to the k-means, isolation forest, one class SVM, but everything was unsupervised as we didn't know what our irrational entity looks like. And after that, once we identified certain anomalous behaviors as definitive, that is, these are the threats, and that's how we actually got hold of the semi-supervised approach. So a very small data set was labeled and a large chunk of data that was still unsupervised. And that's why we thought that deep autoencoder could be a good way of handling that particular situation. And eventually, once we had a good number of labeled data, we opted for RNN to solve the problem. So this has been a journey from rule-based to unsupervised to semi-supervised and eventually to the supervised way of doing things. The tools that we use for doing this is scikit-learn. So when we talk about one class SVMs and isolation forest, scikit-learn is where what we used. When we talk about k-means, then we have used Spark MLlib that has the implementation. And when it comes to autoencoder and RNN, PyTorch is something that we have used. So as you can see, all these tools are open source and free to use. Now, as model training is done and we need to actually now manage the model also. So MLflow is the tool for doing that. It is also open source tool for managing machine learning lifecycle. So MLflow is a platform to streamline machine learning development, including tracking experiments, packaging according to reproducible learns, and sharing them and deploying the models as well. So it offers a set of lightweight APIs that you can integrate into any custom-made UI that you are going to develop for the model management. First thing it provides is the MLflow tracking. So it's an API to log parameters, code results in a machine learning experiment, and compare them in an interactive UI. So UI is inbuilt for MLflow. You can just use that. Next is MLflow project. It's a code packaging format for reproducible runs using Conda Docker so that you can share machine learning code with others. Then we have MLflow models. It is a model packaging format and lets you easily deploy the same model in diverse execution environments. And finally, MLflow model registry. So it's a centralized model store and gives you an API to actually access the model, move the model from development to staging or production, or to even archive the model as well. So to get all these functionalities, we used and we chose and we used MLflow in this case. Now let's talk about how we visualize the anomalies. So when it comes to visualization, we used Apache Superset. It provides a near real-time dashboard. So these are the three things that it provides. You can explore the data, load the data into Apache Superset, and you can actually use the inbuilt ready-made visualization graphs to actually explore the data. You can view your data, so you can create your custom dashboards. We'll show it in the demo how to create such dashboard, and you can actually constantly monitor it in near real time. And finally, you can view and finally, of course, investigate. Few of you might have used dbeaver, which is a data visualization tool. So you can do similar stuff with Superset as well. There are multiple databases that it supports. So there is Amazon, Redshift, Druid, Snowflake, etc. I actually ran out of space, so I didn't include all of them. But all those DBs which support SQL Alchemy, they actually can be integrated with Apache Superset, which can be directly powered by the database itself. So you don't have to have a separate REST API layer to expose the data for the visualization. Rather, you can directly pull from the database itself and visualize. So now we have reached the most exciting part of the talk. And it is the last thing, that is a demo. So we shall close the talk with it. So let's start the demo. Now for the demonstration purpose, what we did is, because of the sensitivity of the network data, we created dummy data generator just to simulate the network events. And as we are dealing with the dummy data, so there is no point of running an actual AI model. So we are just replacing the AI engine with a dummy level, and everything else remains the same, right? So we have the Kafka, which is going to ingest the dummy data in real time, and it is going to sync those data back to Pinot data store. Flink also is going to listen to the Kafka topic, which captures the raw events, and it is going to create the profiles of various IP addresses, and it is going to push back those IP addresses profiles into a Kafka topic again, and that from that topic the data is going to get synced to Pinot. Once the data comes to Pinot, we just show that data into superset visualization, right? So that is the flow of the Eagleeye project that I'm going to just show in the next few minutes. So let's look at the data, what the data looks like. So raw network event looks like this. So it has IP address, it has a event timestamp, it has certain flags like whether it is whether it is a file or not, the number of bytes containing into this request, and the state code, that is from which geolocation this particular IP address is actually generating those requests, right? And apart from that, we have the year, month, day, hour, minute, and second. So this is what the raw network event looks like. So in this demonstration, we are going to use exact same schema for the raw network event, and the Flink job is going to listen to this raw network events. It is going to wait for 15 seconds window so that we can show the profiling also. That's why I just kept the window duration as 15 seconds. And every 15 seconds, it is just going to create profiles of the IP addresses, right, from where the raw network events has been generated, right? And the aggregated IP profile looks like the start and end time of the 15 seconds window, right? And then for which IP address we are going to create the profile, and then what is the number of bytes that IP address sent, the number of total request in that 15 seconds window, total number of files that it sent, and the threat level we're just assigning as a dummy level here, right? So which supposed to come from the machine learning model, but as we are using dummy raw data, so we're not running the exact AI models, and we are just assigning a threat level as a dummy level here. All right, so this is the setup that we are going to show. So what I'm going to do is I'm going to start the demonstration from a code perspective. So I already cloned the repository in my system, and so if I so it is up to date with the upstream that we have. And the next thing that we are going to do is we're just simply going to follow the instructions which is already there in the README file. So if you can see that there are total 3 Docker Compose files here. So the first Docker Compose file is which contains all the 4 services as we talked. That is the Kafka, Pinot, Flink, and Superset. The second the second Docker Compose is to configure the 2 Kafka topic with 2 tables in the Pinot. We'll come to that. And the third compose file is for creating the dummy data and running or submitting the profiler, the Flink profiler job to the Flink service. So these are the 3 Docker Compose files, and all we have to do is we have to just build them, and we have to bring them up, and we are going to see the visualization, and once it is done, we are just going to bring them down, right? So let's follow the steps just like this. So first, what we are going to do is we are going to just build the project. So we build the services first, right? Because those are the 4 services that we need to bring up first. So first thing is done. Second one is the Docker Compose, which is responsible for configuring the Kafka topic for real-time ingestion with Apache Pinot. And so that is also done. And the third one is for the dummy data generator and the Flink profiler job. All right, so all the builds are done. So now we are going to bring up the service first. Okay, so let's see what is the status of those. Okay, so they are running. So let's give it probably a probably few seconds so that all the services are up and running, and then we can just use the OABY to visualize whether they're running fine or not. Okay, so now from the link, if we just open this link, so we can actually access the different services through the web UI. So we can see that the Kafka is up. It has two topics: the network event topic, where the raw network events are supposed to come, and IP profile topic, where the the profiled IP data is supposed to come from the Flink job, right? So Flink is going to read from this this topic, network event topic. It is going to do the profiling, and then it is going to push the output to the IP profile topic. And these two topics are supposed to be synced with the Apache Pinot, so that will come next. So we see that Apache Pinot service is also up, and let's see about the Flink. So Flink is also up and running. And if we go to superset, so superset is also going up. So the default username and password is admin, and so we sign in, and that's it. So all the services are up and running, right? So now what we see is in Apache Pinot there are no tables. So first we have to create those two tables, which would be constantly listening to two different topics for recurs to ingest. So let's do that, and that is the purpose of the next Docker Compose, which is Docker Compose initialize. So that is what we are going to run next. So we run it, let's wait for 10-15 seconds, and then we can go back to the Pinot web UI, and we should see the table number of tables change from 0 to 2. Well, so it is now 2. So if we go to the query console, we see that there are two tables that has been created. The network event table. Of course, there is no data because we didn't start the demeter generator, but it has the columns like IP, is file, state code, bytes, year, right? So it is exactly the same schema that I showed you in the presentation. And once the raw event data arrives in the network event topic, it is just going to get synced into this table, right? Similarly, IP profile table also is created, and it is configured with the IP profile topic. Once the data from Flink comes here, it is just going to show up in this table as well, right? So which has the IP address, the number of requests sent, bytes sent, and then window start and window end and thread level, right? So that's it. So we have brought up all the services. We have configured the Kafka topic with the Apache Pinot tables as well. So now the last step is to start the two things. That is, that means we are going to just start this dummy data generator, and we are going to submit a job to Flink so that it constantly reads the records coming into the raw event topic, and it is going to do the profiling, and it's going to push back to the IP profile topic, right? So that's what we are going to do next, and that logic is there in the last Docker Compose file, which is Docker Compose invoke.yaml. So we're just going to run that. So we have run it, and let's see in the Apache Flink. So Apache Flink, we see that one job has been submitted just now. It had available task slot as 1, but now that task slot is occupied by this job, so it becomes 0, and running jobs is 1. So this is what is running. So we can just quickly go in the network event topic, and if we go to view messages, we see that the dummy event generator is also actually generating the events. And this is a typical event network event looks like, which has the IP address, the event stamp, event timestamp, then whether it is a file or not, right? So just the exact raw network event that we showed in the presentation. So from this topic, the Apache Flink is going to read. It is going to profile for 15 seconds, and then the output is going to be pushed to the other topic, which is IP profile topic here, right? So if we go and view messages, then we see that these are the profiles which is actually calculated by the Flink job, and it is going to push to the Kafka, right? So if we look at the Flink job, if we just double click on that job, so we'll see this, right? So network event, right? That is the raw network event, that is the raw network Kafka topic, right? So that is actually serving as a source, right, from which the data is constantly streaming into the IP profile aggregator. So in the middle square, this is actually the Flink job, which is actually running that logic to aggregate and in an accumulator, right? And it is doing the profiling there. Once the accumulation is done, the profiles are created, and that is being sent to another Kafka topic, which is serving as IP profile sync, right? So we have a source, we have a profiler, and we have a sync, right? And in both the cases, the source and sync are just two different Kafka topics. Source being the raw event Kafka topic, and sync being the profile Kafka topic, right? So if we look at the matrix here, so we can see that there are total 249 records has been generated by the dummy event generator, which is coming into the aggregator, the same number, but it is giving output at 45. That means in that 15 seconds window, lesser number of distinct IP addresses present. That's why the number is less, and then those many profiles are being sent to the sync, and eventually we are seeing those profiles in the Kafka topic itself, right? Now, as we did in the second Docker Compose, that is, once the event arrives in those, once the record arrives in those Kafka topics, that they will be automatically synced into the PinoDB. And so let's run something here. So now we see the data here, right? So it is constantly just syncing all the records which is coming into a Kafka topic into the tables. So if we just run a count, so every time we run, we should see it is changing, right? So we see 387. If we run it again, 391, 394, 397, 398, 3. So this is what is happening. And similarly for the IP profile table also. The profiles which are created by the Flink job, which is also getting synced here, right? Similarly, so now everything is fine. We got the profiles here, and we have a threat level. So it is the dummy level that we just talked about, because we are not running a real machine learning model here. So the next step is so far what we did is dummy event network event data is coming to a Kafka topic, which is a network event topic, right? From which the data automatically gets synced to the network event table. This is where it goes, and also that topic is serving as a source for the Flink job, right? Which is constantly getting the records and processing it, and after the expiry of 15 seconds time window, it is just pushing those profiles to another Kafka topic, right? And the other Kafka topic is nothing but IP profile topic, right? Where we are getting the IP profiles, from which the data again goes back to Pino into IP profile table itself, right? So now the next thing would be to just visualize this data into a nice dashboard, right? So first what we are going to do is we are going to add a database. So Superset has support for integration for any of the databases that we can think of, which supports SQL Alchemy. So here from the dropdown we can choose Apache Pino, and the URI that we are going to use is something that I already posted here. So we just copy this, and we're going to paste it here. So the connection looks good. Then we are going to connect. So we have connected. The next thing is we are not going to build the data in a dashboard from scratch. So we already have the JSON, something that I have already put in the repository. So we can go to settings, we go to import dashboard, we go to choose file, and then we are going to go to this threat hunt dashboard, which is there in the repository, and we upload. So we uploaded the dashboard, and once we open, this is what the dashboard looks like. We can set a auto interval for 10 seconds. That is, every 10 seconds it is going to refresh the dashboard, right? So far 703 network events have been generated. Per second it is around 4 requests that is being exchanged in the network. And then total files sent over the network is 231 so far. Number of files exchanged per second is 1. These are the raw event that it looks like. This is the geographic distribution, right? From California, 64 requests has been sent, from Texas to 93, and so on, right? Now, if we look at the other tab, that is the aggregated network data. So far 131 profiles has been created, right? And this is a typical IP profile looks like. So this is the window start, window end, and all the details about it. Now this is interesting. That is every 15 seconds we are actually building those profiles, right? And here, if we see that it actually just aggregates the data that is in the past 1 minute, right? How many IP addresses we identified as low threat, medium threat, and high threat. So this is just a distribution of it, right? So this is it. So this is a semi real-time dashboard that you can see. It is just, getting refreshed on its own, where we can actually set the refresh interval, and that's what we are seeing. So profiles are getting created 15 seconds, so that's why it is not that fast. But in case of raw network events, so every time it refreshes, we should see new numbers here, right? So this is it. So this is the framework we just described, which I started with. That is this one, right? So we actually demonstrated the Kafka, the Flink, the Pinot, and the real-time dashboard superset. All right. Thank you.